and welcome to the June 2015 Regents exam in chemistry. This is a walkthrough of Part C. This part of the exam consists of 20 free response questions from throughout the curriculum. The questions are grouped together with common narrative sections. To skip to a particular question, click on the index button that appears in the upper right corner of the screen. Here is question set 66 through 68. For questions 66 to 68, we're using the following narrative and diagram. The Bohr model of the atom was developed in the early part of the 20th century. A diagram of the Bohr model of one atom in the ground state, very important, for a specific element is shown below. The nucleus of this atom contains 4 protons, 5 neutrons, and here is your sketch. The first 3 questions we're going to be asked to determine the mass and atomic number for the subatomic particle pictured. We're going to be asked to describe the electron configuration of that atom and also to describe what is meant by the excited state and how that comes about. So let's go to question 66. Question 66. State the atomic number and the mass number of this element. Recall that the atomic number is nothing more than the number of protons, and that was given to us right here in the narrative, 4 protons. So the atomic number is 4. And the mass number is a combination of protons plus neutrons added together. So we have a 4 plus a 5. So the atomic mass number is going to be 9. Question 67. State the number of electrons in each shell in this atom in the ground state. Well, there are 2 energy shells here. And we also know that since this is a neutral atom and there are 4 protons, there's a total of 4 electrons. So where are they going to be? Well, the first 2 electrons will always be located in the first energy shell, as long as we're in the ground state and these electrons are in their lowest energy state, which it tells us they are. So there will be 2 electrons in the first shell, and the remaining 2 electrons then could only be located in the second shell. So it's 2 and 2. Question 68. Using the Bohr model, describe the changes in electron energy and electron location when an atom changes from ground state to an excited state. You need to recall that when an atom gains energy, it promotes its electrons to the excited state by having the electrons actually gather that energy. So in terms of energy, the change in electron energy, we can say that electrons gain energy when moving to an excited state. In terms of their location, when they gain that energy, they actually move further away from the nucleus. They move to a higher energy level. So electrons move, we could say, further from the nucleus. Or we could say to a higher energy level. For questions 69 to 72, we're given the following narrative. In 1828, Friedrich Wöhler produced urea when he heated a solution of ammonium cyanate. This reaction is represented by the balanced equation below. We need to appreciate several things about this equation here. We're shown structural formulas for 2 compounds, the ammonium cyanate and the product urea. We can see that they are organic compounds, so there's a little bit of organic chemistry going on here. We're also going to be asked to identify the functional groups located in those compounds. We're going to calculate a formula mass, determine an empirical formula from a molecular formula, and also explain what is meant by a balanced equation. So we're jumping through several different topics here. It's a really good collection of questions. Let's start with 69. Question 69. Identify the element in urea that makes it an organic compound. Well, they started it off with a pretty easy one here. The key element in any organic compound, of course, is carbon. So the answer to this question is simply carbon. Question 70. Determine the gram formula mass of the product. So this is a topic 3 question. It's a formula math question. We have the formula. It's written as a structural formula. But to get the formula mass, we have to count up how many atoms of each type we have and multiply each of those values by their mass values and then add the whole thing up to get the total. So we can break it down this way. We see that there are 2 nitrogens. We look it up, we find that those weigh 14 each. So there's 28 contributed by nitrogen. There's 1 carbon in the picture. Carbon has a mass of 12. There is 1 oxygen that has a mass of 16. and there are 4 hydrogens in the picture. They have a mass of 1 each for a total of 4. And we add up this column, we're going to get our answer, and it should come out to 60 grams per mole. So back on our answer sheet, we only need to write 60 in the answer space. Question 71. Write an empirical formula for the product. The product is the urea. An empirical formula means that we're going to express the number of each type of atom in its simplest whole number form. Since there's only 1 carbon and 1 oxygen, the simplest whole number form is going to be exactly what you see here. The order really doesn't matter how you write this. There is a more correct way and a less correct way, but the Regents is not really going to care as long as you get the numbers right. So let's collect our parts and write them in. Being an organic compound, I tend to like to start with the carbon, followed by some hydrogens. There are 4 of those. There are 2 N's, and there's an oxygen. So this would be a valid answer. Not the only valid answer. You can put them in again, whatever order you prefer, but your final answer has to have the right number and types of atoms. And question 72, explain why this balanced equation represents a conservation of atoms. The conservation of mass is going to state that we have to make sure that our reactants and products have exactly the same types and numbers of atoms. So if this is indeed a balanced equation, and they tell us it is, all we have to state is that the equation has equal numbers and types of atoms on both sides of the equation. So that's a pretty good statement that sums it up. Questions set 73 through 75 based on this rather complex looking narrative, but I think you'll find that the questions are a lot easier than the narrative. Rubbing alcohol sold in stores is aqueous 2-propanol. There's the compound for the aqueous 2-propanol. Rubbing alcohol is available in concentrations of either 70% or 91% of 2-propanol by volume. So there's a concentration by volume. To make 100 milliliters of 70% aqueous 2-propanol, 70 milliliters of 2-propanol is diluted with enough water to produce a total volume of 100 milliliters. In a laboratory investigation, a student is given a 132 milliliter sample of 91% aqueous 2-propanol to separate using the process of distillation. 3 questions will be asked here. To answer the first, you need to really understand what a mixture is. To answer the second, you have to understand different methods for separating mixtures. And to answer the third, you're going to have to understand this concentration percentage by volume value that they've given to us in the question. Let's go to 73. Question 73. State evidence that indicates the proportions of the components in rubbing alcohol can vary. Well, the composition of the mixture, let's take a look at it. We're told that the mixture can come in 2 different concentrations. There it is right there. It can either be 70% or 91%. So the composition of the mixture can be 70% or 91%. There's your evidence. They come right out and tell you right in the first sentence. Question 74. Identify the property of the components that makes it possible to use distillation to separate the 2-propanol from the water. Well, you have to know what distillation is and what it's based on. Distillation is the process of separating mixtures based on the fact that the portions of the mixture have different boiling points. So, identify the property of the components. They have different boiling points. Now I know they didn't tell you this in the narrative, so this is one where you really have to just know the definition of what distillation is before you walk into the test. Well, if you know that, that's all they're asking you for here. So the narrative really is unnecessary information to answer this question. Question 75. Determine the maximum volume of 2-propanol in the 132 milliliter sample. The 132 milliliter sample is described right here, and we're told that it is 91% alcohol. So we need to find out from the percent composition formula, table T, percent composition by volume is equal to the part divided by the whole times 100. So the percentage is 91%. The part is what we're looking for. The whole is 132 milliliters, and times 100 will round this off for us. So if you solve for x in this problem, you're going to wind up with the correct answer, which is 120 milliliters. So 120 over 132 would represent a 91% solution. Question set 76 through 79, based on this very simple little narrative and a collection of information. A sample of seawater is analyzed. The table below gives the concentration of some of the ions that are found in the sample. So our seawater seems to contain chloride, sodium, magnesium, sulfate, calcium, and potassium ions. And here are the concentrations in moles per liter. We're going to be asked to consider a chemical formula for an ionic compound that forms from these ions. We're going to do a concentration calculation in molarity. We're going to be asked to talk about the ionic radius of some of these ions, and we're also going to be asked to discuss the behavior of these particles as they were dissolved into the seawater. Let's begin with 76. Question 76. Write a chemical formula for one compound formed by the combination of potassium ions with one of these ions as water completely evaporates from the seawater. Since the potassium is a positive ion, it's going to seek out a negative ion in order to form a crystal as the water is evaporated. So we're looking for a combination with either the chloride or the sulfate ion. So if we take our potassium ions, we combine them with the chloride ions, we have a nice +1, -1. Crisscross, we're going to get just potassium chloride. Or if we put our potassium with the sulfate ions, the -2 charged sulfate ions, we crisscross those, we're going to get K2SO4. So which one do you want? It doesn't matter. You can put either answer in the space. I'll go with the simplest one, KCl. You could also answer this with K2SO4. Number 77. Determine the number of moles of the sulfate ion in a 1,400 liter sample of the seawater. We're asked here to use the concentration of the sulfate ion to figure out the total number of moles. So it's a molarity problem. And let's just grab the information from our chart. The sulfate ion has a concentration of 0.028 moles per liter. The formula from table T is that the molarity is equal to the moles of solute divided by the liters of solution. Well, we know our molarity is 0.028, and we don't know our moles of solute. That's what we're looking for. And our liters of solution is a gigantic 1,400 liters. So to solve for x, we simply multiply 0.028 times the 1,400, and if you do it correctly, you get 39 moles. Question 78. Compare the radius of an Mg2+ ion in the seawater to the radius of a magnesium atom. So the magnesium 2+ ion is different from the magnesium atom. In what way? If we know that, we'll be able to answer this question. You can see I've set up the answer to the question with a blank in it. So no matter what I decide, whether it's bigger, smaller, or the same, I'm still going to use the same wording in my question here. So sometimes it's a good idea to kind of chart out how your answer is going to be presented. At any rate, the magnesium 2+ ion became a magnesium 2+ ion by losing 2 electrons. Those electrons were lost from the valence shell. And when we contracted that particle by removing its outermost electrons, it became smaller. So the magnesium ion has a radius that is smaller than the magnesium atom. This is going to be true of all of your monatomic positive ions are smaller than the atom from which they were formed. If we were dealing with a negative ion, it would be the opposite, because those atoms are gaining electrons, thus becoming a little bit larger. And the final question in the set, using the key in your answer booklet, which I've shown you here below, draw 2 water molecules in the box showing the orientation of each water molecule toward the calcium ion. So we have to draw 2 of these little structures here, little Mickey Mouses, in that box somewhere so that they correctly depict the orientation of the molecules. Remember that the water molecule has an uneven distribution of electrons, so that the oxygen side will have a negative polarity while the hydrogen side is positive. Remember that opposites attract. The calcium ion we are shown here as a +2 ion. So the side of the water molecule that's going to be oriented toward the calcium is the negative side. It's the oxygen side. So as we draw our little pictures here, we have to make sure that the oxygen atom is facing the calcium, and the side with the hydrogens is away from it. So there might be one water molecule, and here's another one. The only thing you have to make sure of in this picture is that the oxygen sides are facing the calcium, and that it's very clear that the hydrogen side is away from the calcium. So this would be a good answer. Nice drawing. And question set 80 to 82. Based on the following, a scientist bubbled hydrochloric acid through a sample of water. This process is represented by the balanced equation shown here. The scientist measured the pH of the liquid in the flask before and after the gas was bubbled through. The initial pH was 7, and the final pH was 3. Three things we're asked to do here. We're going to have to identify the acid based on its chemical formula, interpret acid and base indicator results, and also calculate the concentration difference based on pH values. Let's go to question 80. Question 80. Explain in terms of ions why the gaseous reactant in the equation is classified as an Arrhenius acid. We actually don't even have to look at the equation to answer this. If we understand and know our definition for Arrhenius acid, an Arrhenius acid is anything that produces hydrogen or hydronium ions as the only positive ion in the solution. But to be thorough, the gaseous reactant in this equation is the HCl gas, which you instantly recognize as an acid. It's hydrochloric acid. So the HCl gas produces H plus ions in solution. We could also say H3O plus ions if we wanted to, and we could expand on this if we wanted to, but this is the plain and simple answer. The hydrochloric produces hydrogen ions in solution. Number 81. What would be the color of brome cresol green if it had been added to the water in the flask before any of the hydrochloric gas was bubbled through the water? Well, the initial pH of the water was 7. So we are going to go to our common acid-base indicator chart, table M, look up brome cresol green, and read the color at a pH of 7. The pH of 7 is above the high end of this range. So we would go with the color listed on the right-hand side, which is blue, and we're going to come back and write the word blue into our answer space. Question 82. Compare the hydronium ion concentration of the solution that has a pH value of 3 to the hydronium ion concentration of the water. The water, remember, has a pH value of 7. So there's a huge difference here. It is interesting to note that they're not asking you for the actual concentration, they just want a qualitative description. Is it more or is it less? Well, the pH value of 3 is a much stronger acid than the pH of 7, and acids produce hydronium in solution. So the simple answer is the hydronium concentration is larger than the hydronium ion concentration in water. So the pH of 3 is a lot larger. If they had asked us to be more quantitative about this, remember that each time that pH changes by 1 point, the concentration of hydronium ions changes by a factor of 10. So the pH of 3 actually has 10 to the 4th power times more hydronium ions than the pH of 7 does. And for the final set of questions, 83 to 85, we are going to be looking at some redox. A small digital clock is powered by a battery made from 2 potatoes and some household materials. The potato clock battery consists of 2 cells connected in a way to produce enough electricity to allow the clock to operate. In each cell, zinc atoms react to form zinc ions. Hydrogen ions from phosphoric acid in the potatoes reacts to form hydrogen gas. The label diagram and the balanced ionic equation show the reaction, the materials, and the connections necessary to make the potato clock battery. So they've given us the entire redox reaction down here. That'll be very helpful when we get around to the questions. So, 3 questions. We're going to analyze the dynamics of this electrochemical cell, identify the oxidation reaction, and construct an actual half reaction for it. And then we're going to be asked to analyze the redox reaction that takes place in the electrochemical cell. Question number 83. State the direction of electron flow in wire A as the 2 cells operate. You can see that wire A is connected to a zinc-coated nail and a copper rod in the other potato here. So we're comparing the activity taking place on the surface of the zinc-coated nail and on the surface of the copper rod, and we want to know which way the electrons will flow. To answer this question, we can either look at the equation or, remember, in Table J, we're given the series of activity for all the different metals, and you can clearly see that zinc is listed way above copper on Table J, meaning that it is stronger. In other words, it has a greater desire to be oxidized. So the zinc is going to be oxidized here, and the copper is going to be reduced. And that's confirmed by our equation. As zinc goes from having no charge to having a +2 charge, that's an oxidation process. You should also recall that electrons will always flow from the anode to the cathode. Okay, so we're going from anode to the cathode. And the anode is the site of oxidation, and the cathode is the site of reduction. Remember the red cat concept. So electrons will go from anode to cathode, the site of oxidation to the site of reduction. Oxidation is happening on the zinc, so our answer is zinc to copper. Or left to right, if you'd rather. Question 84, write a balanced half reaction equation for the oxidation that occurs in the potato clock battery. Okay, so our half reaction for oxidation, we established in the previous question that it's the zinc that undergoes our oxidation process. So we start off with Zn, and we end up with Zn plus 2. So how do we get from a zinc to a zinc plus 2? We lose 2 electrons. The correct way to show that is to put the electrons on the right-hand side of this equation as products. It would also be acceptable to the Regents if you wrote minus 2 electrons on the left-hand side, but we'll stay with the more acceptable version, plus 2 electrons. You can represent your electrons with a little e minus. You can write the word electrons if you want, or you can put the symbol e, 0 over minus 1. So this is the way our equation should look. It is an oxidation reaction showing zinc being oxidized. And finally, question number 85. Explain why phosphoric acid is needed for the battery to operate. Go back into the narrative and let's see exactly what the phosphoric acid is doing. Here it shows up in the narrative. That's the only place it's mentioned. And the sentence says that hydrogen ions from phosphoric acid react to form hydrogen gas. So the phosphoric acid is supplying hydrogen ions for your equation. So let's simply say that and we'll call it a day. The phosphoric acid supplies hydrogen ions. There are some other things you could say that would be accurate here. You could say the phosphoric acid is acting as a salt bridge. But stick with what is most obvious. The hydrogen ions are coming from the phosphoric acid. And that concludes Part C on the June 2015 Chemistry Regents exam. Look for additional videos for Parts A, B1, and B2 of this exam. Thanks for watching. You can access additional videos and materials for this and other chemistry exams at alchemtutor.com. For questions, comments, or permissions, please contact me at my email address at asnyder@alchemtutor.com. If you have interest in contracting tutorial services, you can also contact me through the web at alchemtutor.com.